Great, thanks, Jennifer. Thank you, everybody, for joining us today. It's always fun to work with Jennifer and do these Earth Data webinars, and I really appreciate you joining us from wherever you are. So today I'm going to talk about DAMET, the version 4 data. And we're going to look at discovering this data, accessing the data, getting it to what some might call analysis ready, and then doing some spatial analysis in Python's geospatial packages, and also within the Esri ArcGIS suite. And I'd like to thank Rupesh and Lane for contributing to this. I have the pleasure of working with Rupesh here at the DAC. And Lane, as Jennifer mentioned, is part of our NASA ArcDAC collaboration and also works for Esri. So thank you both for your help with this. Just quickly, the overall objectives of the webinar today, I really want to work on lowering the barriers to obtaining subsets of gridded multidimensional data that are available through web-based services like OpenDAP. And I'll use the DAMET version 4 data heavily throughout this, but just to point out that any data that's exposed through OpenDAP or Threads or Hyrax are typically available through similar subsetting capabilities. So look for that opportunity. And then just introduce Python's Xarray and other geospatial capabilities in performing spatial analysis on these multidimensional data sets. So really focusing on sort of that multidimensional aspect of these data, the X, Y, and Z, X, Y, and time in our case with DAMET. And then a fun notebook that Lane provided looking at Esri's multidimensional raster functionality. So the content I'll quickly go through and then jump into the notebooks just to introduce the ORNL DAC and DAMET and the DAMET website. And then we're going to go up kind of a level to the NASA Earth Data Find Data website. And that's where all of NASA's Earth data is, including the DAMET data sets. And then we'll jump into the notebook workflows. So an overview of the ESDIS Distributed Active Archive Centers, or the DACs. There are a number of DACs located throughout the country. We are here at the Oak Ridge National Laboratory in East Tennessee. And the DACs are sort of domain specific, and the ORNL DAC's mission is to assemble, distribute, and provide data services for a comprehensive archive of terrestrial biogeochemistry and ecological dynamics. So that's the real focus for the ORNL DAC, is that terrestrial and ecology data that NASA Earth Data Science collects and we distribute. So let's talk a little bit about DAMET. If you're not familiar with DAMET, it is a gridded daily meteorological data set, and it's derived from land surface weather station observations. So it is based on those observations. Some of the data characteristics, the temporal resolution is it's a daily data set, and the spatial resolution is 1 kilometer. The years available are 1980 through 2020, and then I've squeaked in there that we also have 2021 data, and I'll talk about that in a second, about our lower latency product that we're distributing now. The spatial region you can see in the images is North America, including Hawaii and Puerto Rico, and the primary format of these files are NetCDF. And then the DAMET variables are 2 temperature products: the maximum and minimum temperature, shortwave radiation, vapor pressure, snow water equivalent, precipitation, and day length. So those are the variables available through the DAMET datasets. We did release version 4 in December of 2020, so pretty recently. We're excited about that. We do have a publication at the bottom, is the citation for that. So if you're interested in the details, do look at that paper. But generally, the improvements include improvements to the regression model so that we are, for example, doing better at predicting very high levels of precipitation. You can see that in the middle pane, comparing DAMET V4 at the top and DAMET V3 at the bottom for a hurricane event that happened in 2017. So we're doing a much better job at getting those very high precipitation values. We also looked at a reduction in the timing bias of input weather station measurements. And so the graph on the upper right shows time of observation versus the number of station days for the maximum temperature variable. And this is from the weather station data. And so yesterday's, or the Tmax that were taken in the morning, are likely yesterday's temperatures. So we addressed that. Another improvement that we looked at is some of the high elevation temperature measurement biases and looked at improving those. I did mention that we have a lower latency product out, and what we are doing is starting in January of 2021, we are producing the daily data on a monthly cycle. And so at the time of this webinar, January through July daily data are available. They're available as a separate data set. And so you'll search on the DAMET website, or the citation is there on the slide. And questions or looking for DAMET data, just the URL is there, damet.ornl.gov. There are the 4 main collections of data, the daily surface weather data. We do also produce and distribute annual and monthly climate summaries. And then the daily data, the monthly latency is also available. There's the Get Data tab, and we have a number of ways at accessing this data, everything from just directly downloading all of the data. We have a single pixel extraction tool that's very popular, and we'll talk a lot about web services today, and a few other resources there. We also have a learning tab there, and we will put the Jupyter notebooks that we'll cover today on this learning resource. They'll be there in a couple of days, but there are also other notebooks there, not just for DAMET, for a lot of the DAC resources, but we do have quite a few that address DAMET. And then looking a little bit higher at the NASA Earth data search page, if you search DAMET, you will find those collections there. And I mentioned collections because we're going to be talking about collections in the Jupyter notebooks. So a collection is something like the DAMET version 4 daily data. And all of those files within that we refer to as granules, and those are the files within a collection. So you can see that there are over 1,000 different files available from the DAMET version 4 data. So what we're going to do in our notebooks is look at how we can programmatically discover and access those data. And we're going to jump now into the notebook content. I'm going to go through 3 notebooks. The first will outline how to discover the data, access and subset it. Then we'll look at deriving some climatological normals and anomalies from those data from subsets. And then finally, that notebook that Lane shared with us. I'll go through that. Right, so I will jump right into those notebooks. So this first notebook is a tutorial that we're going to pretend that we perhaps work or are studying at the ecology of the Great Smoky Mountains National Park, and we want to get a subset of the DAMET data for just the park. So we don't want to download all of those North American files. We'll look at how we can access this data programmatically, subsetting it before we start working on it. So I included the DAMET overview in this notebook just to be independent of the webinar, but I'll skip through that. and jump right into the tutorial. So the steps of the tutorial, we're going to use a georeferenced polygon file, just a vector shape file of the park to establish the boundary parameters. We're going to leverage the DAMET dataset DOI and search NASA's metadata repository to get a list of files that we want. And then we're going to programmatically download and subset those files via OpenDAP. And then we'll clip the DAMET subset to our polygon region of interest. So let's jump in. These are the tutorials or the Python modules and libraries that we're going to use in this tutorial. So I'm going to go ahead and import all of those right up front, and it'll take a second. So you can see a lot of the geospatial modules and libraries that Python has, like GeoPandas, PyProj, Shapely, and the like. And then I'm going to go ahead and print out the versions of that I'm currently using. Sometimes Python updates will occur and things look different or don't work. So I just want to share which versions of the Python geoprocessing modules I'm using in this notebook. Okay, so step one, we're going to use that vector shape file, or use a vector shape file of the Great Smoky Mountains National Park, a wonderful park here in East Tennessee. If you haven't visited, I encourage you to. But we're going to use that vector file to obtain boundary parameters in order to work on our spatial subsetting. And we're going to use Python's GeoPandas in order to do that. And GeoPandas is a Python library that enables the use and manipulation of geospatial data. So we'll just go ahead and the first thing we're going to do is just read that park file in. And then we're going to list the CRS, the coordinate reference system. And so you can see that this file is in UTM zone 17 north. So we'll need to know that for the next step. And then we just plotted that file up to take a look at it. So we need to reproject this file, and we're going to do that twice. We're going to reproject it into a geographic projection or system, and also into DAMET's system, with coordinate reference system, which is a Lambert conformal conic. And the reason we do that is we're going to use the geographic system for searching NASA's Earth data metadata, and we're going to use the Lambert conformal conic system in order to subset the data for OpenDAP protocols. So we'll go ahead and run through that. So it's this 2CRS that allows us to reproject the UTM into the WGS84. And you can see that we have the minimum and maximum X and Y in latitude and longitude. And then we're going to go ahead and save that to a Python list. And then we're going to do a lot of the same thing. It looks very similar, except this time we're going to define the DAMET projection and then project the vector file into the DAMET projection. And you can see that we have the min and max X and Y in meters in this case. And we'll go ahead and plot those up just to take a look at them. So one in geographic and one in the Lambert conformal conic projection. So we have now the bounding boxes that we need to search and subset these data. The next thing we're going to establish is a time range so that we can use that to access the API. And we're also going to establish the DAMET variable that we want, which is precipitation. So we set a start date for the beginning of 2010 and an end date of 2011. Okay, so this is the point where we're going to start leveraging NASA's Common Metadata Repository, or CMR API, to search for DAMAT data within the spatial and temporal region of interest that we just defined, the park boundary, and for that time period. And so remember that the higher level data sets are called collections, and then the files within those are granules. And one thing about the Earth data collections is that they are each identified with a specific concept ID. So we're going to leverage that opportunity to discover the data that we want. So we'll go ahead and do that, looking at searching NASA's Earth data collections for DAMAT version 4 daily data. And again, this concept ID is a NASA Earth data. It's a unique ID for the data set collections, and NASA has thousands of data set collections. And so this is a way to identify the one collection we want, DAMAT version 4 daily data. And we can do that building a request URL with the DAMAT version 4 data DOI. And so we're going to leverage Python's request library to do that. So we'll go ahead and run that. So here's the request URL and the webinar watcher if you want to explore that. I encourage you to do that, but what we're going to do is we're going to search that request URL and we're going to look for this collection ID, and that's going to be the concept ID that we need. And there it is right there for our DAMAT version 4 data collection. All right, now that we have that concept ID, we're going to search all of, within that, we're going to search and find the files, the specific files that we want. So recall, we want files that are within the Great Smoky Mountain National Park boundary and the time period that we requested. So I just want to review for everybody out there what variables we've defined so far. We've got our time range, we have our precipitation variable, we have that bounding box that we got from the vector file, we have our concept ID, and the CMR URL that we'll need for the API. So we'll go ahead and build this request URL, and we're going to call it Granule Search to create a listing of all the granules or files in NASA's Earth data holdings that fit our search criteria. So we'll go ahead and run that, and this is the request URL, and you can see it now contains the spatial area that we're looking for and the time period that we're looking for. So again, using Python's request library, we're going to go ahead and provide that URL, Granule Search, to create a listing of all of the files in NASA's Earth data holdings that fit that search criteria. So we'll go ahead and run that. And in this case, we have these two files that fall within the search criteria. So in other words, this array, Granule Names, now contains the two files that we want that have data within the Great Smoky Mountains National Park for our time period. And remember, that data collection has over 1,000 files. So we were able to narrow that down to these two files. Okay, so now that we have that array called Granule Names, we're going to go to the next step, and we're actually going to look at how we can download and subset data through the ORNL DAC Threads data server. So this is a link to our data server. I'll go ahead and open that up just so you can see. So this is all of the data that are within the DAMAT version 4 daily data. Let me go back up to the top. So this is the daily surface weather data. So what we're going to do is we're going to programmatically access all of these files and subset the files that we are interested in. And we're going to do that through OpenDAP. And let me just pop into one of these files and then open up. Here's an OpenDAP access. And this is the data URL that you're going to see that we're going to provide in our query. So that's where that comes from and what it looks like. And instead of manually filling all this information in, we're going to do it programmatically and subset the data that we want. So to do that, we're going to use Python's PyDap library, and we're also going to use Python's xarray library. And these are the calls that we'll make, and also keep in mind that we have the granule names array that we saved above. We have our polygon of interest, and we have our time range of interest. So we'll go ahead and run that. And this is, I'm going to let this spin for a minute, and while it's running, let's take a look at, here's the threads URL that we just looked at and our granule names, that we're looping through those. And as we loop through those, we're using xarray's select capabilities to subset those data from the minimum and maximum X and Y that we obtained above in the Lambert conformal conic projection. And as we're doing that, we're also concatenating this file. So for each of those years, we're building a new file that will contain all of the daily data for those years. Okay, so that has finished running, and let's go ahead and take a look at. So this is visualizing one day, the sixth slice in the array of that data set. And I went ahead and put the park boundary on top of that, just so that you can see how that fits into the Great Smoky Mountain Park boundary. And let's take a look at the whole file. So this is a way that xarray can display this data. And one thing to look at in particular is the time. So this is 2 years of daily data. So the time contains 730 time steps, and that's 2 years of daily data. We can also open up that and look at that here. And then we'll quickly take a look at, and I won't explain this too much so that we have time to jump into the next notebook, but we'll look at clipping the subset area by polygon. I'm going to run through this quick for the sake of time, but we're going to use raster IO in order to transform the parameter we want to convert the polygon into a mask, and then we'll go ahead and mask that data. And we can visualize that, and you can see that that now has the data clipped to just the park. And this last step is just another way to clip that data and also to save it off into a GeoTIFF file. A lot of people like GeoTIFFs. So that's what this does. Okay, so I hope that made some sense, and we're going to go into the next notebook, and I'm going to run through that a little bit quicker, but we're going to do another subset, and then we're going to build some climatological normals and anomalies from that subset. So this time, instead of accessing the daily data, we're going to access the monthly data. And we're going to subset to an area, a much larger area. We're going to get CONUS this time. So our source data are the monthly climatologies, also the daily data, but what's being distributed on the monthly latency. So I won't spend too much time on this, setting this up. We're going to set it up very much the same way. We're going to use a shapefile, this time a CONUS shapefile, and we'll take a look at the coordinates reference system. It is geographic, but it's on a NAD83, so we'll go ahead and project that to WGS84 and get the Python list that we need for CONUS that has the minimum and maximum latitude and longitude for that bounding box. We'll also, while we're here, do the same thing for the Lambert conformal conic projection, getting the bounding box that we need for the min and max X and Y. And then just print that out real quick. You can see those two files in both the geographic coordinate system and DAMET's Lambert conformal conic projection. We'll set up our time period of interest. This time we're looking from 1991 to 2020. So we're going to get 30 years of data, but this is the monthly data, not the daily data. And we also set up the DAMET variable to be Tmax. Okay, so we're going to create a monthly normal for the month of June for CONUS from the DAMET version 4 monthly climatologies. So we'll step through that. The first thing that I want to do is looking at one file, and we're going to look at Tmax, the monthly average for 1991. So I'm gonna run this, and I'm gonna look at that one file, and I can do that. I don't have to download this file. I can use, once again, I can leverage OpenDAP and Xarray's ability to look at this data so that I can get to know this data. And you can see that one file has 12 time steps, and what that is each monthly average for this variable and this year are in that one file. So I know if I want June, I'm going to get the June period here. Okay, so now we're going to look at the monthly climatologies by searching through NASA's Earth data, and we're going to do a very similar request as we did above. We're going to get the collection's concept ID, and then knowing that concept ID, we're going to be able to search all of the granules, all of the files to get the to get a list of the files that are within our search parameters. That is CONUS and for that 30-year period. So I'll go ahead and run that. And here's the URL for that. And then just to remind everybody what our search parameters are. Having all of that, we can now build this request URL and obtain our granule list. So we'll go ahead and do that. That's the one I wanted. You can see how quickly that ran, and it's searching for our time period and our bounding box and giving us data, giving us the files that we want, just a list of the files starting in 1991 through 2020. And you can see it's listing both the NetCDF and the GeoTIFF files because both are provided, and we'll access just the NetCDF files. Look at how to do that. Okay, the next step is to, now that we have our list and our parameters that we're searching for, is to subset these data. So we can build the same kind of PyDAP, and leveraging Python's PyDAP and Xarray, we can leverage OpenDAP and build, once again, the same kind of file that we did earlier, but this time it's going to contain 30 years of average June maximum temperature for 1991 to 2020. So a couple of extra things that we need to do in here. We're going to search just for the NetCDF files, and we're going to use the time slice just to subset the June files, and we do that here. So we're using the search year, the start year, which we gathered here, and then we're searching just for June. And we're going to concatenate all of those files and end up with a pretty ready data set in a pretty short period of time. I'm not going to run this block in the webinar. It does take about 7 minutes to run, but I do provide the block here for you to do that. But I have saved it off as a NetCDF file that will open later. So I want to spend a little bit of time looking at Python's Xarray, and I'll run through this quickly. Xarray is really an exciting Python package that makes working with labeled multi-dimensional arrays. Um, this is from the Xarray page. It's simple, efficient, and fun. And I think that too. I think it's really an exciting opportunity to work with multi-dimensional data. So I just want to quickly run through a few things that you can do with this. We'll go ahead and open the data set that we saved above. We'll go ahead and take a look at that 30 years of June monthly average data. So you can see that, you know, the time is 30, X and Y. I can tell this is a subset because the North American files are 8,000 by about 8,000. So that subset to CONUS is there. We can look at this through Xarray's HTML representation. We can look at just the time coordinate. You can see that we have 1991 June all the way through 2020, that June file. So we were able to concatenate all those files. We can look at just the data variables. We can look at the dimensions for the Tmax variable. And of course, we wanted to a plot of this. So we're looking at one time step, the 10th in the array, which is the maximum temperature for June of 2001. And you can dig into the individual, the NumPy array for that. All right, let me jump down here. So I'm kind of in a little bit of a detour here, looking at some Xarray functionality. You can use the iSelect just to subset on positional indexing and get for this one X, Y location, all of the monthly June averages that we collected from this data set. One thing with the DayMet data set is that it is projected, and so you can't put the latitude and longitude in there. This is going to give me an error because the latitude and longitude aren't dimensions. So what we need to do is similar to what we did earlier, and just as an example, I grabbed Portland, Oregon, and according to Wikipedia, this is the lat long of Portland, and I'm going to convert that to DayMet's projection so that I know what its XY is. And then I can use the select on X and Y in order to know where it is I'm selecting. So in other words, I can get this Portland, Oregon, and pull out the values in from our big file for just that one point. So if you're interested in, we get a lot of questions about the projection and how to work with the projection system. So that's one way to do that. Okay, so let's get back to calculating our climatology from our CONUS subset of the annual average maximum temperature. And using Xarray's computation, it really allows a simple aggregation or data reduction on these data sets. It's very exciting. You can, you know, it allows us to apply operations over a dimension by the name of it. And so here in this block is the code block for deriving the average over that 30-year period, which we define as a normal. So we'll go ahead and plot that up. And there you go. So that is subsetting and you know, using Xarray, getting that average over time and getting this 30-year normal maximum temperature for June for the period 1991 through 2020. And you can also save this off to a netcdf file using this to netcdf command. So we're going to quickly calculate a June anomaly, and we're going to access the DayMet lower latency files. So we can go through the same process as we have earlier. I won't run this. It does take a little bit of time, but this is subsetting the June daily file. And then quickly, I'm going to calculate the anomaly just by subtracting. I'm going to derive the average June from that daily file for 2021 and subtract it from the normal that we just created. And I have those saved off for the sake of time in the webinar, but we'll go ahead and open those up. And then here's how to derive the June normal. You can subtract one file from the other. And I'll go ahead and run that. And then we're going to clip that similar to what we did earlier. Just a CONUS. And we'll go ahead and plot that up. And there we go. So this is the maximum temperature anomaly for June of 2021. And as you know, this past summer was a pretty hot summer, especially for the Northwest. So I plotted up that point of Portland, Oregon that we created earlier, and we can select on that point, and you can see that the average June was about 4.5 degrees Celsius warmer than normal. So I'm going to end the webinar there. Well, I'm going to end this section of the webinar, and I'm going to jump into the what's called a pro package that Lane provided for us, and show you some of the functionality within ArcGIS that we have for working with multidimensional analysis. And this notebook is going to walk us through the steps that are in a blog of the same name. And this blog was created by Hong Zhu, also of Esri, who I know have known Hong for a while, and she's been doing a lot of exciting work with multidimensional functionality in Esri software, and has used DayMet a lot in developing some of those capabilities and in sharing those capabilities through tutorials and blogs and training material. So it's fun to see. So basically, this demonstration is going to use the multidimensional analysis capabilities in ArcGIS Pro to understand how climate may affect grape production in California. And we're going to use the DayMet variables of of daily minimum and maximum temperature. And we're going to derive annual growing degree days. And that's going to help us determine over the wine growing regions of California how suitable they are for grape production over the 40-year period. And so working in this Esri functionality is fun. You can jump back and forth from looking at the maps that are created. And this is the Tmin variable, and the Tmax variable is here. You can jump into some of the multi-dimensional functionality within Esri and leverage that in your work. So that's a lot of fun. So jumping back to the notebook, one thing for this notebook, the daily version 4 data for the 2 variables that we're working with has already been subset and clipped to California for those 40 years, 1980 through 2019. So that's kind of an exercise for the webinar user. Now that we've looked at how to do that, you know, you get a vector file of California and leverage those OpenDAP resources and be able to have that data analysis ready for this. An additional step in Esri is to convert these files to Esri CRF format. And CRF stands for Cloud Ready Format. And it's Esri's native multi-dimensional raster format. And there are lots of resources that are linked here to help you do that if that's an interest. So this is the analysis workflow, and I'll go ahead and jump right into the notebook here for the sake of time. So the first thing we're going to do is kind of typical notebook. We need to import all of our modules. We do need Esri's image analyst license in order to perform this work. Get our workspace. The next step is we have these tmin and tmax files already available in the CRF format. So we're going to go ahead and read those into a raster object. Go ahead and run that. And you can see that the time for these two files is 14,600. And that represents the 40 years of daily data. So 40 times 365 is this 14,600. So lots of data in those files. We can look at one time slice. Similar to Xarray, you don't need to know the positional index. You can do that using using the actual variable information. So we're looking at an August day here. We can look at December. So any time slice that you want, you can plug in there. Okay, we're going to go ahead and calculate growing degree days, and I won't read through this, but this is the formula that we're going to do down here. So we have this tmin and tmax multi-dimensional data set. We're going to add those on a daily basis together, divide by 2, and subtract by our base temperature for growing degree days. We've defined that as 10 degrees C in this case. So we'll go ahead and run that. And then the next step in the formula, we're doing this in 2 steps, is this conditional statement that if it's a negative number, if it's less than 0, then we're going to define that as 0. And if it's greater than 0, we'll just fill it in with the daily growing degree day. So if you're an Esri user, you're familiar with those conditional statements. So you can see that these raster files are being added to the map as they're running. And we can pop over here and you can see the time. Time is enabled on these. These are still actually writing. That's why they're not switching to a new day. But we'll let that run. All right, and then we're going to limit. We're going to select the days in the growing season using the logical time values that we looked at before. So we're going to select days that run from April to the end of October. So we're just looking at the growing season as we do that, and you can see that our time slice is narrowed down, representing that. Okay, so the big step here is calculating the yearly accumulated growing degree days. And I'm not going to run this block, but it's a similar function as what we just saw with Xarray. It's an aggregate function. And so the image analyst, that aggregate function is available through the image analyst license, which has several geoprocessing tools to work with multidimensional data. And aggregate is going to generate a multidimensional raster by combining existing multidimensional rasters along a dimension. It's very similar to what we did in Xarray. So we're going to collapse this based on time. And keep in mind, I'm not going to run this. It takes a little bit of time to run, but keep in mind that we're aggregating daily data over a 40-year period. So that's a lot of computing. But we can look at that output. And you can see that our time is down to 40 now. So we have the yearly accumulated growing degree days, which is what we needed to get down to. And the next step is there's something called the Winkler Index, which is a technique for classifying climate and wine growing regions on annual growing degree days, which we just calculated. And this chart shows these regional classes and how they can be classified based on the annual growing degree days. And so we're going to apply a remap, a raster function to remap the yearly growing degree days instead of just those values. We'll go ahead and remap them into these 6 classes. And just before I do that, let's turn off this and this. I think we're looking, yeah. So this is the yearly growing degree days file that we just created. So that is what we're going to reclass. Go ahead and run that. And then we're going to associate those 6 regions. So right now we have just the output values 1 through 6, but we're going to associate those with this raster table. So you can see we have a class name. So we'll change this 1 through 6 into a class name here. And we can view that also on our map. So there we go. And finally, we'll run some statistics to summarize we'll run the summarized categorical raster. It's a geoprocessing tool, and we're going to calculate the areas of the wine class regions for each year. So this is going to create an output table which contains the pixel counts for all of the regions, those 6 regions across all years. And then finally, we'll use ArcPy's chart to display the trend just in 2 of those classes, region 1A and region 1B. And you can see that doing this within the ArcGIS Pro capability allows us to use a lot of the Esri functionality to combine these analysis-ready climate data with a lot of the capabilities within ArcGIS. So that's exciting, and that's a fun part of the ArcGIS DAC collaboration that we can share with you. We know that a lot of folks use open source tools, but we also know that a lot of our data users are using commercial software, including this Esri Geospatial Suite. So Lane, thank you for providing that for us and allowing me to share that with our users in this webinar. And that is what I have as far as notebooks, and I hope that was useful. I do encourage folks to take advantage of the multidimensional data and subsetting and accessing those data programmatically to help make your life a little bit easier. You're not downloading tons of data to your desktop and then working from there. You can have your data in a more analysis ready format and capability by working through some of what was just presented. So Jennifer, I'm going to hand it back to you and I'll stop sharing.